Swayam Prabha. Digital India. Educated India.
Discussing the three-dimensional kinematics. So last time we did some kinematics of some linkages. So some space linkages we have seen. Then let's go to the kinetics part of it. So where we have a body subjected to forces in 3 dimensions. So what will be its effect on the motion? So what we have here is that so if you have forces, so we know that we'll take it to G because all our equations are with respect to G. So all these forces can be made equivalent to this system. And this G, so now this is going to be give raised to, one thing is, of course, is very clear. Let me also show the other side, how I come. So we have, if this is under motion, so we have, say, if this is under motion with a certain velocity and at that instant with a certain angular momentum, so then these forces and moments will give rise to the rate of change of linear momentum, and this is what's, so this is the momentum. So this linear momentum and angular momentum, and if you take the time derivative of those things, so then the applied forces and moment will be equal to that. Okay. So essentially what we are saying here is that the sum of the external forces is equal to mass times acceleration of G, and some of the moments about G is equal to okay. So essentially these are the, ultimately these are the relationships. So the first equation is very simple. So that means that the summation of all the forces will create a motion for the center of mass, and that is related by this one. So actually our problems are more with this the rotational part. So the sum of all the force moments about G is equal to rate of change of angular momentum about G. So this is the one. So if you recall, so we have defined angular momentum. We did it in the beginning of kinetics of 2D bodies. Then we went on to the 2D for quite some time. And so the angular momentum, if you recall, so angular momentum, if you have so the angular momentum, if you recall, so about the origin is given as so this is about the origin, right? And similarly, we can also do it for the G. So we can also do it with respect to G also. So in which case it simply becomes angular momentum about G happen to be this is what we have done. So this is the linear momentum about G, because omega cross rho is the velocity and dm is the mass. So this is the linear momentum, and rho cross is the one taking the moment about G, right? So we have we started off with discrete particles, but then we said that if the mass is continuum, then it looks like this one, right? So that we went on to say the Hg, we have derived it taking the omega and rho as vector products. So we, if you recall, so we put it in the form of the matrix form, we put it, and this is the inertia. So we did this. I'm just recapitulating what we have done. So this is the inertia matrix, because it's a triple cross product, and then we would do this way. Absolutely. Right? That one. And then this is what we got. In fact, sometimes we even represent it as like this one. So I is a matrix, 3 by 3 matrix, and this is a vector, and sometimes we write it. So I can be either about rho or a G. Okay. In fact, just one term, a Gx if you expand. So it is Ixx. And like this, right? So this is what we have. Okay. And then this is a general formula. And then this can be simplified in terms of principal axis of inertia. With respect to principal axis, then what happens is that this will turn out to be, say maybe prime and only this is okay. So where the product of inertias will drop out, okay, So there exists this principal axis of inertia, the symmetric axis, and so this formula will turn out to be much simpler, right? This way, this is for a general body, general orientation of the axis, and this is a special orientation of this axis, x prime, y prime, and z prime. And of course, you know that say if you have a rectangular plate, the principal axis of inertia or all product of inertia terms will drop out. Okay, x prime, y prime are in the plane of the body, and z prime is perpendicular to this one. Okay, and you can find out x prime, say if this is A and B, then so it will come like this one, and IZZ is the addition of these two, and then you can similarly you can find out. Okay, cylinder also we have derived the inertia term, and that's what it is. But if x prime, y prime, z prime, or any x, y, z orientation, then all these terms also will remain. Okay, so now the thing is that this is how we calculate the angular momentum, and we need the time derivative of hg. Okay, so hg as such is what? There, hg is actually with respect to the fixed coordinate system. So we want d dt of hg with respect to fixed axis, right? Everything is fixed axis. But then if you choose certain axis, small x, y, z, something which is maybe having a origin at g, but it is also rotating. So that way, why we want to do is that, what is the problem with this one? If you want to do this one, as I told you once, so if you want to take the time derivative of this one, then this is a product of two terms. So you have the inertia derivative times omega and I times omega derivative. So what happens is that if you keep your x, y, z axis constant, if the body is rotating, then the inertia terms are functions of time, right? They are functions of orientation and they are functions of time. So that's a little bit difficult to handle. So we want to somehow choose another axis where these inertia terms will not change with time. Okay, and however, so at least we want to make our life a little simpler if we choose certain axis other than big X, Y, Z. So if you choose another axis, which may be rotating. Rotating at, say, omega axis. So this is this small omega and big omega. Small omega is actually the angular velocity of the rigid body, and I times that will give you the angular momentum. So whereas if we set up another small xyz axis rotating at some other velocity, so then we know how to do this one. So if then this will be d dt of hg with respect to small xyz, and then we have another term also. It is omega cross. So if hg is measured with respect to small xyz, then what we have here is that So this, with respect to the fixed coordinate system, is equal to the time derivative as measured in small xyz, and then we have another term. So this kind of thing is valid for any vector. We used to take a time derivative of v relative, and then we also have to, now we can even do for omega also. So omega is also a vector. So that angular momentum vector can be measured in the fixed frame, or it can also be measured in terms of small xyz frame. Okay, so this is what we are going to do. So there are situations where we can find out conveniently this big omega, where inertia terms will not change with time. I mean, ultimately what we want is a simple omega, big omega, wherein the inertia terms will not change with time. Of course, angular velocity has to change. That's anyway we want to find out the acceleration. But at least if we don't want the inertia terms to not change, then so this is, we have to make an appropriate choice. So omega has to be, choose omega such that this is always our, such that inertia terms do not change with time. That's number one. Another, of course, this how we choose this big omega so that it doesn't change depends upon the problem. Okay, it depends upon the problem. Like if you have a disk, if it is rotating also, then we can make, looking at the axis about which the inertia may not change. So why I'm saying here is that later on we are going to see some problems like this. We are going to see some problems like this one. We are going to see some problems like this one, where there is a disk mounted. So disk is rotating, as well as the whole thing is rotating about this axis. You understand? So there are two set of angular velocities. One is the disk, as well as the whole thing is precessing about some other vertical axis. So here, interestingly, so we have to see the disk is also moving. So if you look at with a fixed xyz axis, then the inertia term of the disk is going to change. But however, if we say that, okay, I have a set of axes like this, okay, so where there are two ways of doing this one. One is that I fix xyz, small xyz, to the rotating body itself. Okay, so one way of doing it, if we fix small xyz, or either I should be a little bit more careful. Let small xyz rotate at omega. So what happens? I can even say that I'm fixing small xyz to the body itself. Okay, I can even say that, but to be a little bit more careful, I said that there's an small xyz which is rotating at the same angular velocity of the body itself. Oh, so what is the rotation of body with respect to small xyz? Nothing, right? It's zero. So it's something like, if you have in the linear velocity, if I have body moving, I have another set of axes which is also moving at the same speed as this one, then that means that relative to this set of axes, it is having a zero velocity, right? So the same thing can be said here also. So if body is rotating at small omega, okay, and if I have another set of small xyz axis which is also rotating at the same small xyz, then relative to small xyz, then the body is in a state of rest. So that means that with respect to small xyz, if I can find out the inertia terms, will they change? They will not change, right? So in this is one simple thing, that if you fix the set of small xyz axis with on the body, or it's rotating at the same speed as the body, then what do we call it then? So that means that omega is the same as omega. So the rotating frame small xyz is also rotating at the same speed as the body itself. Okay, so in such case, then the body is relatively at constant with respect to small xyz, and then the inertia terms will not change. So that's one trick we make. In fact, it's not our trick, right? Okay, it's done by Euler. Okay, so if you do this, then I will come to the other one. Actually, this is one simple way. Another simple way is that omega need not be omega. Another case is that big omega, we have a small xyz, but it is not rotating at the same speed as the body. It is slightly different, but still what we want is that the set of axes, the inertia terms with respect to small xyz are not changing. So why will it happen? So for example, here, let me explain it to you. The same thing. So if I have a disk here, so if it is a rough body or something like that, so if I have x prime y prime fixed to the disk, and it is also rotating at the same speed as the disk, so then what will happen to the inertia terms? They will not change, right? They will remain constant. But on the other hand, so this is a very simple disk, very simple kind of, it has an axisymmetry. The disk has an axisymmetry. So here, I just want to keep x prime y prime. So if I keep x prime y prime constant, okay, but still the disk is rotating. So what about the inertia terms? It will not change because of the symmetry of the disk. Okay, the disk is rotating, my small xy is fixed, okay, in some form, and then, so since it has a symmetry, so its inertia terms are not going to change with time. So that is also is okay. So one thing is that if you attach, if small xyz is rotating at the same speed as the body, that is fine. Okay, that's very good. So there is no inertia change in the inertia terms. But on the other hand, it's not always necessary. We can always choose for some other kind of simple bodies, omega need not be, big omega need not be equal to small omega. It can be some other thing. Okay, so then that is also is okay. So let us see these things. So I'll show some, the expressions are slightly bigger. Yeah, so this is what I was showing. Yeah, I went through this one just now. So if you have principal axis of, then the inertia matrix will turn out to be a simple diagonal. And okay, I'll come to this problem. Yeah, so this is the one where I have written. So if you have this equilibrium equations, so where H is given by this one, I omega, and then this I omega is like this. Yeah, this is the one which I was talking to you. I'll make this PPT available to you. I'll send it to you. In fact, I've sent one thing earlier, but then this is slightly concise version. Okay, so this is what I'm saying. So if small xyz rotates one thing is, if it doesn't rotate at omega, so then you have the expression where, so this, if you expand this one, so then this is what you are going to get. Okay, so this is the derivative with respect to the small xyz, and whereas this is the second term of big omega cross hg, and this is the 3 terms. Okay, but however, the simplification of this one, which is if big omega is as small as small, yeah, if it is, so still you can, the expressions are slightly longish, so we have to live with. That's why I just made the slides. So here, this is, if you expand all these things, vectors, angular momentum, because angular momentum is a, if you remember, it is a 3 by 3 matrix multiplied by the angular velocities. So that you put it into this one, and then you can simplify it. So this is what you get. This is the last one, is the one which I was talking about. If xyz are the principal axis of inertia, so that means that only the diagonal terms of inertia terms will remain. Okay, you have chosen small xyz as the principal axis of inertia itself. Then the all the cross products will drop out, and this is the one nicely in a smaller form. So that way is there are two situations where big omega may be equal to small omega, big omega is equal to small omega. So it depends upon that type of problem. If you have small, simpler problem, so then big omega need not be small omega. So these are the Euler equations of motion, okay, about the principal axis of inertia. So I'll just tell you this one. This is a small problem. How to calculate, just to start with, we will see this problem where we calculate simply the angular momentum. After this we will go for the derivative of the angular momentum. Okay, so in this we have chosen a rectangular plate attached to the rod, but not just exactly perpendicular to the rod, but it is at some angle 45 degrees. Okay, and now the rod is going through the center of the plate, but at an angle, and then the plate is set in motion about the rod. So the rod, the angular velocity, there is a certain angular velocity there for the rod, and the rod is, the plate is rotating along with the rod. So here then we have all kinds of inertia terms. So let us just see. So here we have chosen x prime y prime in the plate, and z prime is perpendicular to the plate, but the axis perpendicular to the plate doesn't coincide with the axis of the rod. Okay, it is obviously at some angle 45 degrees. Okay, so if it is rotating about with a certain angular velocity omega about the z axis, so then it has components about y prime and z prime. The angular velocity has components. Or we can even find out, first of all, finding out the inertias. I think it's a small exercise for you. So finding out all this x prime, y prime, y prime, y prime. And the choice of this x prime, y prime, z prime is because they are the principal axis of inertia. So the inertia terms are very simple. Okay, so if that is the case, then the angular velocity, because it is I inertia terms with respect to x prime, y prime, z prime axis multiplied by the angular velocity. Okay, so like here, what is it? Yeah. So if you want to find out hg here, So this is in the matrix form. Okay, that's also is there in the next slide. So this inertia terms are with respect to x prime, y prime, z prime axis, and we can find out very easily. They are all 1/12 ml square. Okay, and then about z prime, it is the sum of x prime inertia plus y prime inertia, and only the principal axis. And then we needed the angular velocities about x prime. About x prime it is 0, so the y prime and z prime are the two axes about which we have the angular velocity component. So essentially now it is nothing but, in fact, you can put it in the matrix form. If you are more comfortable, you can put it in the matrix form and then find out what is hgx, hgy, hj. So this is prime. Okay. So is it okay? You can find out. Okay. And this is when you multiply this one, so you get the angular momentum with respect to x prime, y prime, z prime. But on the other hand, if you want to go back to the set of axes, okay, the original x, y, z, and so you can combine them back, and then you can find out the angular momentum about x, y, z axis also. Okay, so I think in fact, if you look at this one, this is z prime and k prime. So z prime and k prime, you can convert them back to j and k. Absolutely. So it's just getting back to any other set of coordinates. Then I think there is something calculation of kinetic energy and so on. So I think I'll leave it. If you want, you can find out the kinetic energy also. So kinetic energy is nothing but omega transpose h. So it can be derived and then you can find out. Okay. So like this, so we have, this is what I was saying. So you can also put it in the matrix form and you can calculate the Hg as well. Okay, whatever I have done here is done here. Okay, so let's get back to again. Now, again, the same plate. Now we want to find out what is the forces that are being applied. Okay, what is the forces that are being applied on the plate? So if you, this is unsymmetrically mounted on the rod. So when you have this kind of unsymmetric thing, then when you rotate it, you are going to encounter certain moments that are being applied on the bearings, or the bearings have to apply certain moments on this one. So exactly here, exactly the same plate now, which is being rotated, but now we want to find out what are the forces or the moments that need to be applied for this kind of motion. So if you go back, interestingly, so what we have here is that the angular velocities are about x, y, z here are given to be like this one, and it is rotating at a constant velocity. So the angular accelerations about x, y, z are 0. Okay, so this is the one which you need to observe. So essentially what we have here is, if you go back to this, yeah. So there are two ways of doing it. One is you can choose x prime, y prime, z prime in the principal axis direction, or here what has been done here is going back to the original thing, because the axis x, y, z are not the principal inertia axis, principal axis of inertia. Okay, so if you just do this, so what happens here? If you want to do the problem with respect to the x, y, z, z is the vertical and x and y are the horizontal axis in the horizontal plane. So these are not the principal axis. Okay, so we can do it. I mean, there are several ways of doing the problem. So this is, in this case, we are just sticking to the x, y, z, the fixed axis. So if so, then what happens here is that the inertia terms or the cross product terms are not zero. So you have xy, xz, yz, xz, and all of them will be there. And then if so, then what you need to apply is the general one, okay, where you have all the terms here, all the inertia terms. Okay, this is a very XYZ is a very general orientation, and you have to then you require the calculation of all the other terms. Okay, in this, if you look here, this is a most general, very big formula. So what is that which are going to be non-zero here for us? So if you look at the input that's given here, so we have W omega x is 0, omega y is 0, only omega z is there. So that way, if you look at this one, there's so many cross product terms are there. And the only term that remains non-zero is the one here with omega z square. Anywhere omega x or omega y is appearing, they are all 0. Okay, only omega z term will be coming into the picture. Okay, so if that's the case, then what we have here is that there's only mx iyz omega z square. That's the only term that's present. Okay, all other terms are. What about my and mz? They are all 0. My and mz have something either omega x or something of omega y, and they are all 0. So of course there is also one term I said, so which is 0. Okay, all right. So this is a very simple mx is iyz omega z square, and what we require is that iyz. So this is an interesting derivation of yz. So that means that you require the product of inertia of yz. So iyz is nothing but integral yz dm, and so you have to do it along the length of the plate. So then this is at 45 degrees, so you can replace z by y, and y square rho dl. So dl can be written as √2 dy, and so everything is in terms of y and dy. So you can do that little bit of integration, and then iyz turns out to be 0.02 kgs meter square. So if you substitute omega z here as 25, so then you get mx as 79 Newton meters. Okay, and so this is mx. So you can imagine. So that means that the axis of mx is on this one. Okay, how do we generate? Imagine that there are two bearings up and down. So there is one bearing, say A at the top, and there's another bearing at B. So what kind of forces are required so that you can create mx? Or in the reverse direction, so the plate will exert that kind of forces on the bearing, and we require forces by bearing to have this kind of motion. So what kind of forces this will exert on the bearings? Will it exert a moment? Let's imagine that there's a one bearing at A at a height of h, and another bearing B here at a height of h below. So what kind of forces it will create, or moments, on the two bearings? Will it create moment, or will it create forces? These are two equal and opposite forces. So let us say, so I have x here coming out. Let us say this is y and x. I have A. So I just looking in the direction of x, okay, and there's a y here, there's a z, and x is coming out of the board. Okay, so and then what we have here is the mx. You require a force mx, right? That's what we have calculated for this kind of motion. So how do we generate this kind of mx? By the some moments at A and B, but it should be free to rotate. Remember, this is rotating. So how do you generate a force mx? This is your old first few classes of statics. How do we generate a moment mx here? Because we have only A and B as bearings. Okay, so bearings have to apply that kind of forces or moments. So what kind of things we require then? So you require this kind of thing. So that means that you require a force here and a force here. And this force should be in the direction of y, right? So that you can generate a moment mx. So how much is Fy? It is mx divided by 2h. So that means that if you require a force of a moment of mx, so that is generated by two equal and opposite forces at the two bearings. I call it F, and divided by 2h, mx divided by 2h. Is it Fy or Fz or Fx? Is it Fx or Fy or Fz? I need a moment mx, right? I need a moment mx for the plate to rotate in a eccentrically mounted way. What is that I require? Please, you done statics so much. Now you're experts. Statics and dynamics. Do I require, is it Fx, Fy or Fz? I know, I mean, the moment divided by the distance between the supporting points AB. Okay. What do you think of here? So obviously it should be in the direction of y. I already wrote my. If I put Fz, let us see. Okay, let us see if if I put not Fz will not create any moment. Fz is in the direction of the axis. So if I put Fx, two equal and opposite forces Fx, what kind of moment will it create? Because that's also, will it create a moment in
Y direction.
Exactly. That's good. So if it is, so obviously, right? So if you have forces, two equal and opposite forces, Fx and minus Fx here, then it will create a moment about pi. Okay. So since we require a force mx here, so it will be equivalent to two equal and opposite forces at the bearings of Fy. So you require that kind of force to be applied on the plate, or on the other hand, you can say that the plate will be exerting that kind of opposite forces on the bearings. Okay, the plate will be exerting an opposite force on the bearings. Okay, so please go through. Yeah, this is using the matrix thing, and then I would like to do the whatever the gyroscope which I have showed as an example. So this I'll do tomorrow. Okay, I'll stop here.